Okay, so we go back to the place where we stopped the previous hands-on session. So what you see here is the kind of case we would like to, we hope you will be able to do on your own now after learning. So this will be simple lid-driven cavity, which means the mesh is simple box. It can be more complex with some more resolution in the corners and less resolution in the middle, or it can be a simple uniform square of the length of 1 with the velocity. 3 boundaries are wall, 1 top boundary is Dirichlet with the velocity of 1, plus we have those step functions at the end from both sides, just to avoid some crashes due to discontinuity. The spectral method don't like any discontinuity, so we don't do this. We simply smooth out mesh using a step function, and you are actually provided with the step function math step underscore step. So now I can go to the code to show you how it's actually worked. How does it work? You have under workshop examples, when we go to the workshop examples, there is directory lid-driven cavity, and there is only source directory. So there is a missing mesh directory and run directory. And under the source directory, source, you have the makefile underscore user.inc. So that is a way to make file to compile. So you have the make information for make, how to compile the file called math underscore tool. That's what you are going to use. And when you look into the file math underscore tool, you see that the first function is actually a step function. And this step function goes from 0 for x equal or smaller than 0 to 1 for x bigger or equal to 1. And that's here. Everything which is smaller than 0, step function is 0. Everything what is bigger than 1, step function is 1. And somewhere in between, some exponential smooth function to fill it in. So that's what you have. And that's what we expect to do, is to use the step function to smooth out both ends for the Dirichlet boundary condition on the top, and to provide mesh, user file, and run. And to do this, you use the existing example, which is provided by us, which means it's an flow past cylinder. So because there was some question, not everything was clear. So I will go through this example again, pointing a little bit what could be changed, what could be different, and then we could leave you some time to make an example. So we of course start with the Gmesh, and straight away from the beginning you see that my Gmesh mesh for the flow past cylinder is much more complex, because each of those small sections here I was meshing as a separate section. In your case, it's enough to have one section, one square. But let's go back to the code of the flow past cylinder. That means under workshop examples, let's go back to the external cylinder with Gmesh. And let's go again to see what is what. Let's start with the source, with the compilation. So you will have to copy more or less everything from here. I can do the compile clean, compile script clean. So that's what's necessary. That's what you will have to copy and, of course, change. The first change, of course, will be about the compile script, because here, you see, I don't compile any additional files. I provide the name of my case, which here is external cylinder. That would be something else. It's not so important. Position of the Nek code, the same. Compilers will be the same. Pre-processing list will be the same. But the user file, of course, has to be changed. The same you have to add from the source under the lead-driven cavity, the make file user.inc, which contains the information. What we have when we look into the user file here, we have all of the interfaces which are necessary. First of all, we start with the mesh smoother. I would say for the lead-driven cavity, there will be no need for the smoother. We could take it away easily. And then you have the variable properties, that means density and viscosity. They will not change. This is the same. User F, no forcing, will be the same. No temperature, no changes. This part actually will be different because here we have the object. We will not have any object. So all that would go away, actually. Everything what is here would go away. But once again, going from what we do here to understand, we have a time loop. We are in the user check. This routine is called during initialization once, and then the variable iStep, which is inside include file tstep. Actually, what I could do, I could show you how the tstep include file looks like. So we could do this way. Release or let's increase tstep. So tstep is actually include file that contains all of the information about the time step, the current. There should be somewhere iStep here, a number of steps to be performed, and so on and so on. So this is the include file. We actually are interested in that one, iStep, because that tells me at which point we are during our simulation. During the initialization at the wall, because that's our boundary condition 2, that means at the wall we create the object. During the rest of the simulation, after every step, not every step, because we have here IO output, and we have this user parameter here. So we define actually how often we calculate a torque calculation, which will be written down to the log file, and then with the same frequency, actually, we call HPTS, which means is the probing. We defined a set of probes, and then every time the HPTS is called, we will output to the history file the values of the velocities and pressure at the points which we defined. And we have the boundary conditions. The boundary conditions, of course, for the lead-driven cavity would change, because here we have just inflow on the left and outflow on the right. So on the left, just ux is equal to 1. The rest of the variables is 0. Our initial condition for the lead-driven cavity will be different as well, because there will be no general motion in our lead-driven cavity. So the initial condition should be 0 everywhere. Here, of course, for the boundary conditions, we would need to use a function, a step function, based on the position. And position actually is inside the common block Nek5000, which we have here, include file Nek5000, and this Nek5000 contains X, Y, and Z coordinates. So we'll have to do our boundary condition based on X. That's the variable which we'll have to use for getting the smoothing at the end. And of course, we have as well this version of user.dat. We will not deform the mesh this time, but because our boundary conditions and our mesh was defined inside the gmesh, and then we have to translate a number into a character string, a string of 3 characters. So what kind of boundary conditions we will have? Here we have the wall at the cylinder, we have the Dirichlet boundary at the inflow on the left, and we have the outflow on the right. For the second case, we will not have the second one, and of course the wall will be related to all the walls of the cavity. User.2, here we take access to the solution by putting include soln. We can once again look into what the soln is. Soln contains simply all of the calculated variables: x velocity, y velocity, z velocity. It contains as well the information about the viscosity and the density, magnetic fields, pressures. All the variables are accessible through include file soln, and that is why we have here include file soln, because for outpost I'm using the velocity, pressure, and temperature, and that is why I need this include soln. But in case of flow past, in case of lid-driven cavity, there will be no smoothing, so there will be nothing in user.dat. And then we have the routine to estimate a Struhel number, which is simply based on the single position in the mesh and looking into the time variability of that of the velocity in that point. This routine will not be needed for the lid-driven cavity. There will be no Struhel number calculation in this case. So we went through the user file. We more or less know what it is. We know how to compile it. Simply compile script minus all. That will give us the code. Okay. Then we have to go back to the mesh, because we have to produce mesh. How the mesh for external cylinder is made? Once again, you will have to modify this geo file, this script, but from the beginning, it's kind of clear that all those things which are here are not necessary. If you will use, because what they contain information about different parts. Once again, let's look into how the mesh. Do I have somewhere the zoom in to the mesh? No, I don't. Okay, so how the mesh looks like, it contains of the number of different sections, and each of those sections is given by the parameter. So that is why inside my flow path cylinder geo file, I have so many parameters. All of those will not be necessary for the case of the lid-driven cavity, because lid-driven cavity is simple box. And if you will use the uniform resolution, the whole box, there will be no parameters at all. If you would like to have the higher resolution at the corners, you can have one parameter with progression inside the domain. But you can start simply from the simple case when you have just one box. In that case, you don't need all those parameters. Everything what you need is this element scale, because that's actually variable, because that's actually required when you define a point. What you will have to do is to follow this section and to generate set of points. And this new point tells you where x, y, and z coordinates are generated. And then the last variable is actually a scale. And this variable is given here. However, for us, this scale doesn't matter because we will not change, we will not let GMesh to make the meshing itself. We will do this on our own. Then actually this part is unnecessary. You simply have to generate 4 points. And then when you look here, you can generate a list of points from, you can combine points into lines. And how, you know, first of all, how because I've never asked, what is your knowledge about GMesh? Should I explain this as well? I never, maybe I will should simply go through this. You see, I'm keeping a list of the variables. You can keep it as a list, or you can keep it as a point, as a single variable. So for example, here, point PTS center is a variable that will contain a value of the new created point. So you see, I always generate everything in the same way. I first store the information about which point I'm creating. The new point shows here and here, and then I'm creating the point with the same number. So what you will have to do, you will have to be like points left corner, point upper right corner, and to copy this 4 times. Then for given list, for given set of points, you can generate a line connecting this. 4 lines can be connected, and you know, this is actually a proper way of doing this. I'm creating a list and then simply adding the new part of the list. 4 lines can be combined into a single surface, and everything is some kind of reproducible. You have new point function to get a value of the new generated point. You have new line function to get the number of new generated lines. So this new line will again generate the new line connecting 2 points, PTS squared 2 and PTS squared 1. Here I'm doing the operation which are not necessary for the lead-driven cavity, because I'm simply doing the replication or extraction of different edges. This will be not necessary. What will be necessary is actually this part. You have to once again your surface call as a fluid, and then you will have 2 boundary conditions. One will be the wall, so you need the list of the 3 lines that will be a wall, and 1 will be actually your Dirichlet boundary conditions. The top line will be the Dirichlet boundary conditions. The rest is unnecessary. And then if you will use very simple case without any progression, then you will need just one transfinite with some number of splits that go split all 4 lines. And then you will have the surface transition. And this part is unchanged, maybe except the file number. You can change the file, the name of the file number. So this, once again, one can simply, after you have this file, you can simply generate a mesh by calling gmesh and the name of your file. And with the minus at the end, it will not start the interactive mode. This produces the, in this case, excel.mesh. This is a ASCII file. It could be a binary as well, and in this case, it doesn't matter. So we'll not go through this in details. But what we have to do, we have to convert it to, I think it was like this, to Nek format using converter, which we already compiled and stored under Nek bin. So we give the dimension. It will be the same dimension for the lead-driven cavity. You could have different file number. Here is, of course, ext cell. And now we know here it is a list of the boundary conditions. Now we know that we have some periodic boundary conditions. You will not have those periodic boundary conditions in the lead-driven cavity. So here it will be just 0. But for flow path cylinder, we have the one pair of periodic boundary conditions. It's the bottom, which is 6. We go to top, which is 5. So we go from 6 to 5. And because the distance between bottom and top of my domain is 30 units, so we don't move in X, we move by 30 units in Y, and we don't move in Z. And then we have our RE25. And the only thing we have to do now is to generate map file. So ext cell to provide the relative radius. We have a map file, and this way we finished everything, because all this stuff can be copied to the run directory. We already ran this. We already looked into we executed, so we have the output. Now we can look into the ext, the history file, and you see that the beginning is the same. First line contains the number of points, then you have the coordinates of the points you have chosen, and then for each of the points, every time you called it, you have a section which every line contains the time, Vx, Vy, Vz, at the point that corresponds to the position in the block. Because you see everything is divided into the blocks. So we have the first block, the second block of the 5 values, and so on, and so on, and so on. And of course, with VisNek, we could visualize, I think did we run VisNek? Yes, we did. So we can look into ext cell Nek5000. We see that we have ext cell file. We start from the first file. We have the 6 snapshots. We can visualize it with visit or paraview. Simply, okay, that shouldn't go this way. Simply by opening the file, it's on SCOG-snap for me. I need a path. I open the metadata file here. It directly opens and uses the proper reader, and then I can simply visualize like velocity, or maybe not magnitude, maybe x velocity, and then we can see it growing. Of course, it's just a few time steps, so not much to see yet, but we can visualize the pressure as well. We can actually do some additional stuff, because when you look at our list of the files, you see that we have, in addition to those SMH, that means mesh, the smoothing before and after. So if I would like to see those two, okay, first of all, I will go here back. I can simply edit my ext cell.nek5000. and add here SMH, simply to add the pre-tech SMH, and we could reopen it. And of course, there is nothing to be shown, but what we can do actually, we can show the elements. So that was our element structure before smoothing, and that's after. Okay, I think we can stop here. And I think you can start to do your lid-driven cavity case. Is it okay? Or are there any more questions?
Mm-hmm. Okay, but then I guess it would be now time that you could try to work on the lid-driven cavity, modifying as Adam outlined the external cylinder case, and we three, Nicholas, Adam, and I are in the room. And if you have any questions, just let us know. And then, depending on how general it is, we can take it up in the big room, or we can also go into a breakout room. But I will now stop also the recording, and now it would be time until 4 o'clock for you to work on that and identify possible problems. Okay.
Okay, so my solution to this problem is slightly more complex in the sense that I wanted to have higher resolution in the corners of the domain. So instead of having one big surface, one big block covering the whole domain, I divided this into 4 blocks with the additional point in the center, and then I splitted each of those blocks into some number of cells with some progression. So let's go to the code. We can later on as well add the solution to the repository. I have 3 directories: gmesh, run, and source. Let's go to the gmesh first. Once again, lid-driven cavity, Joe. Okay, let's lid-driven cavity geo. I'm using actually 2 variables here. One is the number of cells every of those 4 elements is splitted to, and then I use the parameter for the progression. So those are my parameters. And then I have additional parameter which is hard-coded, which is a box size, and you can see that actually I changed a little bit. I don't go with my box from 0 to 1. I go from the box, my box from -half to half, simply to have shorter code for when I will calculate a step function. And then once again, a scaling parameter is unchanged. And then I have a list of points. I first initialize my list to empty list, and then every time I add 1 point to the list, and I generate the point. So I have 9 of those points because I have 4 squares. Then I do the same. I initialize empty line list, and then every time I'm joining 2 points, I simply add 1 line to the list. So then I get horizontal lines, vertical lines. So at the end, I have 12 lines. And then I once again, I initialize empty surface list. Then for each surface list, for each set of lines, I generate a curve loop. Here I have to be careful about the orientation of the line. So as you see, some of the lines are with minus at the end. And after having a curve loop, I'm simply adding the surface to the list and I'm generating the surface. I generate 4 of them, and after I have 4 of them, I can start to provide the information about the physical properties. That means those information that will be at the end written to my mesh file. So first of all of the surfaces, which all the 4 squares I've built, will be called fluid and will have the property 1. Then at top, which are actually in my case 2 lines, which are 2 horizontal lines on the top, are the Dirichlet, condition 2. And then I have a wall, which actually consists from the 6 lines which are around my box. After that, I perform a single division, but in my case, the progression is not 1. That means that it's not a uniform resolution, but I have some given progression. That means I have to be careful about the orientation of my lines. So some of my lines are simply negative here, but all those are simply positions in the array, the number of the lines. After providing information how all the lines are splitted, I split all of the surfaces, and then I recombine the surfaces, meaning that I give the information to Gmesh that everything should be a square. There should be no triangulars. And the rest is exact copy from the Excel, except the change in the name. So that's how it works. We can now run it. And you can see how my domain looks like. So there are 4 squares. There is some progression. So I have higher resolution at the corner, lower resolution in the center. So that's my mesh. I should have the mesh file as well. Yeah. So now I can convert it. So 2-dimension lead-driven cavity. I have 2 boundary conditions and no periodic boundary conditions, so everything is fine. So now I can genmap. So it will be lead-driven cavity and 1% as a relative error, a relative radius. So now I can copy the lead-driven cavity RE2 to run, and I can do the same with the map file. Then I go to the source. What have changed in the source? The size file is exact copy from the Excel. We already had math_tools.f. I'm going to use one subroutine from there. The makefile user was already here, and it contains the makefile directives for compilation. So what I've done, I've simply modified slightly the compiled script, changing the name and simply adding the information that math_tools will be compiled. No more changes required here. Then when we go to the lead-driven cavity user, the beginning of the subroutine doesn't change because there is no forcing, no changes here. The user check is empty because actually I don't perform any calculation of torque here. User boundary condition is actually slightly modified. I had to define that my math step is the real function. It was not necessary because we didn't talk about 477 so much, but here there is no implicit none, so there is explicit type definition. So actually, math step would be real anyhow. I've defined a few more information. Let's say, what is my box half size? What is the size of the domain where I have the smoothing, that means the step function actually takes part, I simply calculate the relative position, and then I'm using the value of the step function as my velocity component. And actually, that's all. There are no much more differences, except that, of course, I had to update my definition of the boundary condition. So I have the Dirichlet, which is 2, and wall, which is 3. And that's actually everything what was changed. So one can compile it. And we can go to, we actually can, first of all, I have to copy Nek5000 to run. We can go to run. So what do we have? We have the code, we have the connectivity information with the, we have the mesh, and the lead-driven cavity runtime parameters. I've changed number of steps to the 10,000 because those actually are short. I adjusted the length of the time step in this case for my specific mesh. This has to be done for a specific mesh, no other way. And I as well changed the Reynolds number. So the Reynolds number is actually, because it's negative, that means it's Reynolds number to 1000 to have some faster evolution. And now I can simply run it. Nek binary running script, that means Nek BMPI, lead-driven cavity, which is the name for processors. And now I can look into the log file. So yeah, the CFL is around 0.5, which is fine. The time step is constant for this simple simulation. The simulation has ended. So once again, visnek, Nek bin, visnek. So we can look now in lead-driven cavity, Nek5000. Yes, everything is fine. We can take a path. Okay, we can take this here, open. Okay, I open the metadata file. Okay, and let's say we take velocity magnitude. We can see the evolution. And now we see that we already reached kind of steady state. At the end, we can as well look at the mesh. So I have slightly higher resolution at the corner, lower resolution in the center. Okay, I think that would be everything. Are there any questions?
There's one question in the chat.
Okay, yeah, I see. Of course, you know, everything will be three-dimensional mesh in Gmesh, and you will do everything in 3D. Actually, we were doing this kind of stuff for one of our AMR cases when we used the tilted 3D cavity. To break all the symmetries, we built 3D cavity and we rotated it. So there was no symmetry direction there. But of course, everything depends on the setup.
Okay, but then I guess if there is no more questions for today to Adam regarding this this homework, I guess we are 10 minutes after 4, and we have now been sitting here since 9 o'clock. So I think it would be also a good time to conclude this tutorial for today. We will also post this the results that Adam now just presented on the homepage from the course, so you can download it from there, so that you have a complete set of the results, the slides, and as soon as I have converted the recordings, they will probably also be uploaded there. Yeah, I guess that is it from our side. Jing will send out an email to you with a short course evaluation with a number of questions, and of course it would be nice if you could answer there whether there were some parts that or some things that you may want to improve for the future. Just let us know what you thought about today's tutorial. And well, apart from that, I guess we would like to thank you for participating, and in particular I would like to thank Adam and Nicholas for their very nice presentations for today. And yeah, I don't know, Jing, is there anything else that we should add now at the end?
No, thanks. So
okay,
everything fine.
Okay, very good. But then I guess thank you for participating. We hope that you will use Nek5000 at some point in the future, and check back to the homepage where all the course material should appear during the next days. Yeah, thank you very much. Thank you and goodbye.